Okay, so for today's video, Charis, we'll begin to deal with the dual pivot. I mean the quick sort algorithm. So for the quick sort, it is a sorting algorithm based on the divide and conquer that picks an element as a pivot and partitions the given array around the picked pivot by placing the pivot in its correct position in the sorted array. So meaning we will begin to sort everything, but there will be a specific partition that we'll begin to base with works by selecting a pivot element and partitioning the array into two subarrays. It could be the right and left subarrays with elements less than the pivot and another with elements greater than the pivot itself. Now, in this one, there will be steps. You have to choose a pivot, partitioning, then recursion, and base case. You will be going to deal with the recursive algorithm as well. So for the pivot selection strategies, we're following here the first element, last element, random element, median of three, middle element, median of the array, and the dual pivot. So for that one, we'll begin to deal with the first element. For the first element, that is definitely the simplest pivot selection strategy where the first element of the array is chosen as the pivot. And you have to choose the first element as the pivot. You have to partition the array so that elements are smaller than the pivot go to the left and all our largest element go to the right. So you can definitely check that in the videos right there, how we're able to deal with that pivot method for this first element then. And for this, next will be the first element. There will be a best case time complexity will be the ON log(n). That happens when the first element always results in balanced partition. It is then in splitting the array into the nearly equal halves. So that's the average time case will be the ON log(n), the same thing. Works well for randomly ordered data, but still susceptible to imbalances splits. And then for the worst case, that happens when the array is already sorted, then you will begin to sort that in reverse. So each partition leaves one side empty, leading to n recursive calls instead of log(n). So definitely it will become quadratic time for time complexity of n squared. Then for the space complexity, that is logarithm of n. Recursive calls depend on the depth of partitioning. In the worst case, completely skewed partition, it may take linear space. And for the last element, this approach is select the last element as the pivot. Then follows the standard of quicksort partitioning process. For this step, you have to choose the last element as the pivot. Then you have to partition array such that the elements definitely smaller than the pivot are placed in the left and elements greater than the pivot are placed in the right. It depends on the partition that we are using actually. Then recursively apply the quicksort to the left and right subarrays, the same thing. So for the best case time will be ON log(n). That occurs when the last element divides the array into nearly equal halves at each step. That is somewhat similar to the first element. So it works fine for randomized input, but does not guarantee balance for that one. And here for the worst case time, it will be quadratic still. The same thing happens when the array is already sorted, and if you will begin to sort it in reverse, and that degenerate into a linear chain of recursive calls, making it inefficient. And afterwards, the space complexity will be the logarithmic of n. In the worst case of linear stack depth if partitions are in balance. Excuse me. And then we'll be going to have the random element. We select a pivot instead of always using the first or last element. So it will be random here. So choosing a random element as the pivot, swap the randomly chosen pivot with the last element, then that's how you will work. For example, you were able to choose the element at the middle. You have to swap that into the last element so that you can definitely go ahead and continue the process to use the center partition function as well. Partition the array into two parts, the same thing. Elements smaller than the pivot go to the left and greater than go to the right. That's our goal. Recursively apply the quicksort to the left and right subarrays. That means to say, you can continue after you were able to swap that at the last element. Now, the best case will be the linearithmic or ON log(n). If lucky, random pivots create perfectly balanced partition. And for the average case time, it will be the same thing, n log(n), which on average, randomly chosen pivots prevent worst case scenarios and perform well. For this one right now, if for the worst case times complexity will be quadratic, it is very rare but possible if random select Sean keeps producing highly skewed partition. For this one, the space complexity will be O logarithmic of n, the stack depth. And for this one right now, the median of 3, it is a method used in quicksort to select a pivot that is more likely to result in a balanced partition, reducing the chances of the worst case performance. So the steps that we're following, we select the first element, middle, and the last element. So determine the median, the middle value of the 3. After you are able to identify the 3, you will begin to sort that out and what will be the median and the 3 elements. So swap the medium element with the last element so it can be used as pivot. So as what we did earlier, if you were a I mean, in the other videos that you have to swap the middle element into the last element so that we can do the process of the quicksort. Then you have to partition the array so that elements smaller than the pivot go to the left and elements greater than the pivot go to the right. So the same thing. Then recursively apply quicksort to the left and right subarrays. Here now, the best case time complexity for the median of 3 will be O(n) log n. The same thing that helps ensure better balance when sorting the random data. Then average case times complexity will be the same thing. That is very effective for large dataset as it avoids worst case scenarios. And for the worst case time complexity that is quadratic is still possible but less likely than choosing the first or last element. And for the space complexity, that is still the same thing. That is logarithmic of n, which is only a few extra comparisons are needed to find the median, keeping extra space minimal. And afterwards will be the middle element that helps reduce the chance of imbalanced partition compared to always picking the first or last element. In this case, we will begin to select the middle element as the pivot, which is calculated as the middle low plus high divided by 2. So you have to definitely 0 plus the high, for example, 0 plus 7 divided by 2. That's how you will deal with that. Swap the middle element with the last element so it can be used as pivot. You have to swap that in the last element as well so that we can definitely continue the process. And partition the array such that elements smaller than the pivot go to the left and elements greater than the pivot go to the right. The same thing that you have to do it recursively. Apply the quick sort to the left and right subarray. The same thing that will happen. For the complexities, for the best case time complexity will be and again the same thing. If the middle element creates near equal partition, then the performance is optimal. And for the average case time, it will be still the same thing. Perform similarly to a random pivot, but still susceptible to bad luck. And for the worst case times complexity will be quadratic, the same thing. If the middle element is always the largest or smallest value in recursive calls, it leads to unbalanced partition. So for the space complexity, that is a logarithmic of n uses no extra space apart from the recursive calls. Next will be the median of the array, ensures that perfectly balances partitions, leading to an optimal quicksort performance. So first step, we have to find the median of the array. Enter array, sort the array. First, you have to create a temporary array, then you have to sort it. Then select the middle element right there. You have the n divide 2 for that one, for an array size of the n. So it will be basically a lot of a process for this kind of for this type of median of the array. That is totally mess. Then swap the median element with the last element so it can be used as the pivot. So you will go to the original array. Then you have to partition the array. Elements are smaller than the pivot, go to the left, and elements greater than pivot, go to the right. So this is really a lot of works to do. Recursively apply quick sort to the left and right subarrays. So for this one right now, here for the median of the array, it will be the same thing O(n) log n, since the exact median always splits the array evenly. Since we're able to identify the sort, then we're able to sort it in using the median of the array, then you will begin to sort it. That is, it's totally make no sense for doing that one. However, just to consider for consideration, if how does it really work? So each recursive call halves the problem size. Then average time case times complexity always provide balanced partition, making it one of the best strategies. So as they mentioned, it is best strategies, but for me, it is not a best anymore. And worst case times complexity, it is O(n) log n. Unlike other method, this method never degrades to n squared, but finding the median exactly takes linear time. Using the median of medians algorithm, the total time becomes linear plus the n log n, then is equals to O(n) log n. That's why, making it slightly slower than the other strategies. But of course, I can't definitely appreciate this kind of pivot selection. So for the space complexity will be O(O) log n space, same recursive depth as standard quicksort, but extra space may be needed for computing the median. So for this one right now, there will be a dual pivot as well. It's an optimized version of quicksort that uses 2 pivot instead of 1. So there will be a P1 and P2. Choose the two pivot elements. The leftmost element is equals to pivot 1 and the rightmost element is pivot 2. That ensures that pivot 1 must be less than the pivot 2. If not, you have to swap them, is what I've mentioned in the other videos. You have to partition the array into 3 parts. Elements less than pivot 1 go to the left partition. Elements between pivot 1 and pivot 2 go to the middle partition. And elements greater than the pivot 2 go to the right partition, as what I mentioned to you in the video that I presented. Then, recursively apply the quick sort to the left and right subarrays. For this one right now, there will be the best case times complexity for that one is O(n) log(n). Using 2 pivots, the array is split into the 3 partition instead of 2, making sorting faster. And for average case time, it will be still the same thing, O(n) log(n), faster than single pivot quick sort due to the fewer swaps in comparison. Of course, it will be effective since you can definitely fix that easily. And for the worst case times complexity will be quadratic, rare, but possible pivots are always poorly selected like smallest and largest values. Still in place sorting, so extra memory use minimal. So that is logarithmic of n. Now for the partition algorithm, we are following 4 partition here, naive, Fudamoto, force dual partition. Let's take it one by one. In this partition right now, naive is a simple partition method that is really simple. Method that rearranges the array into 2 sections. There is a left partition, elements smaller than the pivot, and the right partition, elements greater than the pivot. So this is basically good enough. And for the naive partition, the steps, you have to choose the pivot, create a temporary array, store elements smaller than the pivot first, store the pivot in the middle, store elements greater than or equal to the pivot at the end, and copy back the memory array to the original array. So you have to make sure that you will need to do that in your steps as well. So for choose a pivot, you select pivot using pivot selection strategy as what we do have discussed earlier, and create a temporary array. In your temporary array, you have to initialize an empty list to store elements in an order way. In your temporary array, you have to store right there the elements smaller than the pivot first. So traverse the original array and add all elements smaller than the pivot to the temporary array. Then afterwards, you have to store the pivot as well in the middle. Then append the pivot itself to the temporary array. Afterwards, you have to also put as well the greater than or equals to the pivot at the end. So traverse the original again and append all elements greater than or equal to the pivot to the temporary array. If this is vague for you, you can definitely watch the videos for how we could able to do it in a application already. Then you have to copy back the memory array to the original array. Replace all the elements in the original array with those from the temporary array, maintaining the new order. So that's how you will do it recursively. Now for the Lumut's algorithm, it is simple as well, since simple partition scheme which UI chooses a single pivot and arranges the array such that there is a specific condition, which is elements smaller than the pivot move to the left and elements greater than the pivot or equal to the pivot move to the right for that one. So for this one, the pivot is placed in its correct position in the sorted array. That ensures that we could be able to place the pivot in the correct position. So for Lumoto, there will be you have to choose the pivot, initialize a pointer I for smaller elements, traverse the array J from low to high. So you have to keep on running this J, then swap the pivot into the correct position, return the pivot index. So for this one right now, choose a pivot. You have to select element as array high. You have to set this array high using pivot selection strategy. Then initialize a pointer I for smaller elements. For this one right now, you have to set I as low I minus -1 to check the position for the last smaller element because you will begin to increment that one if regarding with the rule later on. Then you can definitely check that in the video already, for the example. Then traverse the array J from low to high -1. That is definitely if array J, if it is less than a pivot, you have to increment I. This is our rule, and swap array I. Then with array J. And if array J, if it is greater than or equals to pivot, do nothing and move to the next element. That's the thing that you will need to do in this partition. Then afterwards, swap the pivot into its correct position, swap array I plus 1 if you are using the last element. But if you are using the first element, swap to I only. So that the pivot is now correctly placed at the next I plus 1, last element pivot. But for first element, swap to I only. That's what I mentioned. So return the pivot index, the pivot new position I plus 1 for last element as pivot, I minus 1 for first element as pivot is returned to be used in recursive quicksort. You have to definitely continue the process. So let's actually take now the horse algorithm. It is really an efficient partitioning method in quicksort actually. moving elements around a pivot, ensuring that all elements smaller than a pivot are placed on the left and all of the larger elements are placed on the right. So ensures that elements are rearranged around the pivot but does not necessarily place in its final position. So in this particular right now, there will be a steps that you have to choose a pivot, initialize at 2 pointers I and J, move I and J until a swap is needed, swap array I and array J, stop when the array I, if it is greater than or equals to J. So if they overlap actually. Choose a pivot, select a pivot element, array low, then initialize 2 pointers I and J, where I low, then leftmost element, then J will be the rightmost element. In order for you to capture it, to understand how does it work, you can definitely refer that into the another videos. For example, move I and J until a swap is needed. Move I to the right until array I. If the rule if array I if it is greater than requested pivot, you have to move. Then move also the J to the left until array J if it is less than or equals to the pivot. So you have to move that one as well. So swap array and array J. If I is less than the array J, swap array both I and J to ensure smaller elements are on the left and the larger ones on the right. So for this one right now, first algorithm, stop when I overlap to the J. When I, if it is greater than or equals to J, stop the process and return J as the partition index. In this particular partition, you are not considering that your um, pivot is already in place. No, that's not necessary here. So for this one, let me also give you the dual pivot. Instead of using single pivot, there will be two pivots are chosen. This pivot divided into the array into 3 parts instead of 2, making the sorting process more efficient. So there will be a step, choose to pivot, partition the array into 3 sections, use 3 pointers, partitioning steps, return 2 partitions, indices. So for this one right now, choose to pivot, the first and last element are chosen as the pivot 1 are low in left pivot and pivot 2 as the array high and right pivot. Ensure that pivot 1 is really less than the pivot 2. If not, you have to swap them as what I mentioned earlier. So for this one, left partition, for the partition the array into 3 sections, left partition element are smaller than pivot 1. The middle will be elements between pivot 1 and 2 if it is less than greater than the pivot 1 and less than the pivot 2. Then right partition which me elements greater than pivot 2, of course. So for this one right now, use 3 pointers. I starts at low +1 next to pivot 1. J starts at low +1 and moves right. K starts at high -1 and moves left. But you can definitely refer that in the video that I've actually presented so that it will be basic for you or simple for you. Partitioning steps, if array J, if it is less than the pivot 1, you have to move it to the left partition. And if array J, if it is greater than the pivot 2, you have to move it to the right partition. So that is really that is necessary. Otherwise, keep it in the middle partition. After scanning all elements, swap pivots into their correct position. So for this one here, return to partition indices, the new index of pivot 1 where it was placed, the new index of pivot 2 where it was placed. So these two indices will be used for recursive quick sort calls in the third partition. That ensures as well that your pivot 1 and pivot 2 will be already put into the right place. So let's actually define recursion. It is a key concept in the quicksort algorithm that we are using, that it means call itself to break down the problem into smaller problems. So we are definitely doing that accordingly, repeat and over again so that we can definitely go and sort it into the base case. Recursive case is the function partition the array, and then recursive is source the left and right subarray. And base case is the recursion stops when the subarray has 1 or 0 elements, meaning it is already sorted. So that's basically explainable. So for the time complexity of naive partition, the best, average, and worst case will be the linear time, since for each element, a comparison and potential swap are performed. In the worst case, all elements are traversed. So the space complexity for that one is there's definitely they're 0, 1 because only a few variables are used to swap elements and track position. So for this one right now, for the Lomoto partition, the time complexity for this best and average case will be the linear as well. It performs a linear scan over the array to partition the elements. Then the worst case for this is different. That is quadratic. The worst case, if the pivot is always the smallest or largest, the algorithm could degenerate into a linear scan per recursive call, resulting in quadratic time. Excuse me. For Lomoto, the space complexity will be still constant because only a few additional variables are used for pivot and index tracking. So that's why. For Hor's algorithm, partition, I mean time complexity, the best, average, and worst complexity will be the linear. Like Lumoto, it scans the array, but it may perform fewer swaps. And for the space complexity will be the same thing, constant, similar to Lumoto, that it uses a fixed amount of space for partitioning. Now for the double partition, time complexity, best, average, and worst case will be linear. And that algorithm scans the array in linear time and can handle duplicates efficiently. And for this one right now, the space complexity, it uses a few pointers for partitioning but does not require additional space. So that's how it worked for the quick sort algorithm.